Yeah, thanks a lot for having me. So my talk is probably a lot less scientific and less sort of mind-expanding than the previous talk. It's kind of a hard transition to make. I think the best way I can think of this transition is we're not going to achieve artificial intelligence without really solid engineering practices. So that's what I'm going to talk about today. I'm going to talk about this open source project, MLflow, which we started to manage engineering around machine learning applications and to make it easier for teams to do that. So just to start with, people have been doing software development for decades now, but machine learning development is often a lot harder than just traditional software development. And I want to talk about why that is, given what we do in machine learning. So I'm just going to compare the two. So one of the first things that you want to look at is the goal. So in traditional software, the goal is usually just to meet some kind of functional specification. If I press this button, this happens. If someone makes this API call, a record is deleted and whatever. In machine learning, on the other hand, the goal is a little bit different. It's not a Boolean, either or we met the spec or we didn't. It's often to optimize some kind of metric. For example, click-through rate or accuracy or something like that. And often you're never really done with it. If there's anything you can do to make that metric better, it means more revenue. It means like a safer car, whatever it is that you're working on, and you want to keep improving it. And so you have to constantly experiment to improve this metric. You never say, OK, we're totally done with that. The second difference is that in traditional software, the quality usually depends only on the code that you wrote. You can sort of try it out, look at it, and see if it's good. In machine learning, by definition, the quality depends on the data because machine learning is programs that generalize from data. And also, it depends on things like the training method and tuning parameters and so on. So you just have to take into account more things when trying to control the quality. And finally, in traditional software, you usually pick one software stack that you're going to work with. For example, there are 20 different types of open source databases out there or whatever, or services, and you debate their merits, and then you pick one and you use one. In contrast, in machine learning, because the goal is to improve that metric, and you want to constantly experiment, you want to be able to compare as many libraries, models, approaches, and so on as possible for the same task, and easily swap in if there's a new one. You don't decide, for example, I'm going to standardize on PyTorch, and then if like a researcher publishes a new state-of-the-art model in TensorFlow, you say, oh, I'm not going to run that because it's TensorFlow. Like, no, you want to be able to leverage the best things that are out there, and that also complicates development. So if your machine learning application is successful, you probably want to use it in production. And there are other factors there that also continue to make it harder. So first of all, you have to figure out a way to keep the application running on new data because it's supposed to learn from data. So you need to set up this cycle where you take your data and you sort of automatically do data preparation, training, and deployment, and all the quality control around that. Often the different steps in this cycle are managed by different people with different areas of expertise. So for example, you might have a data engineer who knows things like Apache Spark and can do that part, a machine learning engineer who knows how to design a model, and then people who actually have to deploy it. And so you need to make sure that nothing is lost in translation between these folks. And finally, the software you use has to work across different environments, and there are also all these different libraries involved. Remember, I said you want to be able to use and mix the very best libraries, and so this problem sort of expands with each library that you're considering to use. So just some examples from people who are working on this. This is a chief scientist at an ad tech firm. So they say, I built hundreds of models per day to increase the company's revenue. Anything that increases that revenue, the ability to make predictions is going to be great for us using any library, MLlib, PyTorch, R, et cetera. And there's no easy way to see what data went into a model from a week ago and rebuild it. So that's a problem because the data matters. And then this is a larger company, so our company has hundreds of teams using machine learning, and we can't easily share the work across them. If a team picks up some code that someone else wrote, it often doesn't even give the same result. So because of these challenges, people have been thinking pretty hard about how to organize the machine learning development lifecycle. And there's sort of a new class of system coming up called the machine learning platform that is meant to do that. So it's a bunch of services and APIs and best practices. And some good examples of these types of platforms are the internal ones at large companies like Facebook's FB Learner, Uber Michelangelo, Google TFX, and so on. So these platforms basically standardize the lifecycle and give you some APIs where if you develop your ML application within the platform, it can automatically manage deployment and retraining and data validation and so on. So it saves you a lot of ad hoc work, which is awesome. And these have been really successful within these groups in terms of enabling lots of applications. But there are also some disadvantages in the way people are doing this now. So first of all, these platforms are limited are often limited to a few algorithms or frameworks that the ML platform engineers want to support. They can't support everything out there under the sun. But as I said, the ML users always want to run the latest stuff and compare and use the best-in-class things. So this is kind of a tension when you have a small team developing an internal platform. And they're often also tied to each company's infrastructure, so everyone is sort of redoing the same class of work. So at Databricks, obviously we have a lot of users, who will do machine learning, and we want to task and we provide these similar benefits, but in an open manner where you don't just have everyone building their own thing internally. And so last June, we launched MLflow, which is an open source machine learning platform. So it's designed, it's Apache 2 licensed, and it's also designed to work with any machine learning library, algorithm, programming language, and so on. And the one thing that we tried to do differently from a lot of the existing platforms is what we call open interface design, which is we tried to make it very easy to plug in any code at all that you have into MLflow and to make no assumptions about what machine learning library or data format or whatever you're using. And what this means internally is that it's all based on REST APIs. You can use those from any language. It's based on things like command line interfaces. You can write your command in any language. So we don't really care whether you're running Python 2 or 3 or R or Java or like whatever else in there, because we designed the interfaces to be at a different level. MLflow has 3 components in its current release. So it tackles experiment tracking with this tracking component, reusable workflow with something called projects, and what we call model packaging with something called models. So passing models between the different groups in the company. And it's also a pretty fast-growing open source community. So we launched this in June, and there are already more than 80 contributors to our GitHub, a lot of very non-trivial external contributions. And we're excited about that because it means, with many people working together, we can build a much better platform than, we would have been able to build alone. And so we've already, we've gotten a lot of really great ideas and inputs from the community. So in the rest of the talk, I'm just going to explain these components in turn to show you how it works, and then I'll talk a little bit about how people are using MLflow. So let's go into the first component, which is experiment tracking. So first of all, how would you do experiment tracking without MLflow? I think everyone who does machine learning has had to do a lot of experiments, but at least in the way I've seen people do them, it's very unstructured compared to the way, for example, a scientist would run experiments or anything like that. So the typical thing is you write a program, it's a script, or maybe it's a notebook or something, and it's got some input, some parameters, like the input file or some tuning parameters in there, and it also produces some results. So for example, it will print out some metrics like accuracy. Maybe it will create an artifact, so a file such as the pickled model, and then you just run this thing in a terminal or submit lots of jobs, and you get this big long list of what happens. Maybe if you're really careful, you'll copy and paste these into an Excel spreadsheet. But as you do this and as you do development, a lot of problems come up. So for example, what if there's some other parameter you haven't tuned yet, and now you want to begin tuning it? In the past runs that you ran, you don't have information about that. And you need to update your data about that. What if you want to upgrade the machine learning library? It's not enough to just capture the parameters you have, but also the environment, what code ran, what dependencies were there. There might have been a bug in it where it was doing poorly, and now it's going to do well. Just keeping track of what version of the code each result was from is difficult. And it just becomes very painful to manage these. And this is even if you're working alone. If you're working in a team, it's even worse. So what does MLflow tracking do? So the tracking component in MLflow is very simple. It's a lot like a logging library, something like log4j or logging in Python. And it's just basically a way to do structured logging of your machine learning models, your machine learning applications information. And it also automatically captures information about your environment, such as, for example, if you're using Git, it knows which Git revision you were in, and so on. All you have to do is import MLflow and run these logging statements, and then you can visualize all the experiments using this UI. It can also be run as a server that you share with other users in your team, and you get this structured view on top of it. If you don't like the UI, you also get an API to just query this data programmatically. So some of the things you can do, just basic things like sorting your runs, clicking on them to see all the data in detail. You can log arbitrary files and artifacts such as an image. You can take notes on the thing and remember more information about it after. So pretty basic stuff, but it's nice to have a structured system where you manage this instead of doing it ad hoc. You can also take a bunch of these runs and compare them. So you can almost have your own little internal Kaggle competition or leaderboard and take a bunch of these results and see what kind of values correlate with good performance and so on. And finally, this sort of open interface philosophy means it's very extensible. So you can log pretty much anything as a file or as a tag on the run. So for example, if you're using notebooks, you can actually log the notebook with all the code and all the cell outputs. If you're using TensorBoard, you can stick all those TensorFlow logs into MLflow's artifact store and pull them out and so on. So very easy to extend with your own stuff. So this is one example of a component where suddenly you and your team can easily keep track of development. The second component is projects. So this is for reusable workflow. It's kind of meant to answer two questions. How do I split my workflow into modular steps that other people can reuse? And how do I run a workflow that someone else wrote? So this is just an extremely simple packaging format for your code and your dependencies that tells other people how they can call it and also tells MLflow how it can set up the right environment. So basically, you've got a folder or a Git repo with your code, and you have this little descriptor file, and it can provide an environment. This can be Conda or Docker, and it can also define entry points that are callable and that have parameters. So for example, when you pass your program to someone, you just tell them, okay, you have to set these parameters, but they don't need to know exactly what command is running in there, or in fact, they don't even need to know whether this is Python or Java or something else. And you can run projects from the command line. You can actually just point to a Git repo and run a project. It's way easier than trying to check out and read someone's README and figure out how to run their code. So that's pretty cool. You can also run them programmatically to put them into workflows. And so actually, we have a bunch of examples where, for instance, we take a project and then we just run hyperparameter tuning over it or things like that. And all that is enabled because you can just call these projects from another program. And the UI also knows how to visualize that to show you what happened. And so that's for sharing your work with others in a reusable way. And then the final component is a similar concept, but for models. So how do I reliably pass my model to production applications? And it's this packaging format, very similar idea for models. And so basically, the idea here is you can use many machine learning libraries, or you can just put in some custom code into your model. And we have this sort of generic format. I'll talk about that in a little bit more detail later. And then there are tools that know how to do various types of deployment or model evaluation, regardless of what you use to build it. So we wrote these tools, and for example, people in the open source community added libraries to save models from PyTorch or from H2O, and all the tools that were in there automatically worked with the new models, because we didn't need to do this all-to-all, like how do you deploy this thing on that deployment mode type of setup. And so one of the things, if you look at model packaging, there are a lot of formats proposed out there, such as Onyx, that support how do you save the weights of the model. But our approach is a little bit different. We really care about people who just want to run this, and we look at it at the level of packaging arbitrary code. So for example, our models can actually declare multiple flavors or ways of reading the model. And one of the ways is just treat it as a Python function. Any tool that's, that treats the model as a black box can use that interface and just call it, and doesn't need to know what ML framework you used or whether it's compatible with Onyx or whatever. And then if you do have something where your model actually is a neural network and it's got weights, it can also declare that. And if some of the downstream tools do something special with that, like map it into hardware or whatever, they can look at that flavor and they can do that. So it's just a way of defining multiple levels of abstraction for the same model. So what does it look like? So again, it's basically a folder with arbitrary files and this little descriptor file. And this tracks some information, for instance, which run ID created it, when was it created, so you can go back and see how it was built. And it also declares these flavors or interfaces. So for example, this one has a TensorFlow flavor. It is a TensorFlow graph, and tools that understand that can load it as a graph and look at TensorFlow specific fields in it. But it also has this Python function flavor. So other tools we have, such as the deployment to Docker or the deployment to Spark, they don't know anything about TensorFlow, but they do know how to run a Python function. So that's how they view it. So that's what's in this one. And again, there's a community building things both on this end and that end that means they all benefit from each other. So a little bit about the project status and how people are using it. So as I said, we started the project in June 2018. It's actually grown a lot. We have 81 contributors now from more than 40 companies, and our team working on this is maybe about 8 people. So a lot of non-Databricks contributors and a lot of pretty major contributions that were given from outside. So for example, a more scalable storage backend for arbitrary SQL databases, Docker packaging, our API that was contributed by our studio, integrations with many libraries, a plugin system that enables users to extend various parts. All those things were done from outside. So we're really excited about the growth. It seems people find this idea of an open source ML platform valuable, and they also found it easy to add stuff into. Just in comparison, for Apache Spark, when I was working on that, it took almost 3 years to get to this many contributors. So we're definitely excited about that. Some example use cases, so these are just very briefly what some Databricks customers are doing. So people are using it in very different ways. So first one here, this is an energy company in Europe, and they basically want to model the energy grid. They have all these power plants, wind farms, things like that, and they also have major consumers like a factory or a city or whatever. They have a small data science team that's doing this. It's about 10 people, but they have to manage and update these hundreds of models. So they use MLflow to set up each model and to track it and to keep track of various metrics. And then people can look at these and see how they're doing over time and see whether anything is going wrong with these many models that are out there. And these models have to be updated pretty much every day or every few hours. The second one is an online marketplace. They actually talked at our user meetup. So this is actually Edmunds, the online car marketplace. And they set up a workflow with, they wanted to have these multi-step deep learning pipelines using Keras and PyTorch. And basically the use case there was when you upload images of your car on Edmunds, they want to figure out which image is the front of the car, which image is the inside. Is this image just an ad that we don't want to to show on the website? Is it spam, and so on? So pretty cool use case to make, to make the website better. And then finally, there's this online retailer who's using the models component to package custom logic and ship it to the deployment team so that the machine learning engineers don't need to make patches to the web application to change the pre-processing logic. They can package it into a single box with the model itself and ship it. There are also a bunch of talks coming up. If you want to see some public talks about this at the Spark Summit conference, you'll be able to see them online as well from some fairly large companies. So for example, Gojek is basically a Uber-like company in Indonesia with it's a major sort of user of machine learning out there. So you can also see some of these. So just to conclude, these machine learning lifecycle tools can really simplify development, both for the model designers and the production engineers. They can simplify that transition, make it easier to run things. And we think the open interface design in particular enables very broad collaboration. And people have been adding all kinds of stuff here that we didn't think about before, like new programming language, and it's it can all kind of work together. If you want to learn about MLflow, it's open source. You can just pip install it and get started locally. You don't need a server or anything, or you can set up a server for your team and have people share it. So thanks, and yeah, happy to answer any questions. Yeah.
Thank you so much for the great tool that for this project.
Okay.
My question is like, from my understanding here is that the project provide like end-to-end flow from like on the way data to the deployments. So if like from the standpoint of the user, how much like involvement in those like process
I see.
Yeah.
Yeah, so the question is how much, I guess, can you as a user be involved in the process, or how much is built in? So yeah, when we designed this, because we had this idea of, hey, it's just some APIs that you can call anywhere, we wanted to give users a lot of control. So if they have their own way of deploying this, they can just use some of the components and APIs and not others. So for example, if you already have a model deployment pipeline, maybe you use our packaging format, but you use the existing software you have for model deployment. So it's sort of, or if you already have a way of running jobs, you can just use the experiment tracking API in whatever system you're running the jobs in today. You don't, as long as it can talk to our server, it can report stuff. So the answer is you can customize how you run things, and we just try to give you these small building blocks that capture, that handle common problems that you can put together. We actually want to build out more in the future in terms of like, a default way to do things if you don't already have something set up. But right now, we try to be pretty agnostic to that.
Yeah. Very cool. And I have another question. Like, do you have any comparison between in terms of cost, how much they applying this, and compared to the traditional?
In terms of cost?
Cost of like user the label that's spent on the effort building the whole pipeline compared to the traditional that like have to build our own.
Yeah, I mean, so it's hard to quantify, but I think, both small and large teams spend a lot of time on setting up good processes and debugging things and maintaining them once they're in production. So it really depends on the domain and stuff, but there are a lot of horror stories about that. And we found, like, we tried to make it something that individual, data scientists or ML developers would just want to use on their own, not something that their boss tells them to use. But yeah, we found that a lot of those just working alone are excited to have stuff like this to automatically kind of track what they're doing and share it with others. So it saves them time even when they're working by themselves. It's hard to quantify how much, but it's definitely, like, I think people wouldn't be using it if it wasn't saving them some time. Yeah.
Thank you so much.
Yeah, other questions?
So
yeah.
One of the questions I have is I saw things like Keras TensorFlow in the MLflow pipeline, like being able to use in the MLflow environment. Does it also include MLlib and help with some of the distributed part in Spark?
I see. Yeah. So basically, the way it works now is this part here with model packaging. We provide APIs and plugins that can save models from a lot of popular libraries. So that's where we have these integrations. If you have a library that's not supported, you can always wrap the model in a Python function and you can still save it, so or in an R function or whatever. So you can also use other libraries, but these are just built-in things so that in one line you can save a TensorFlow model or load it later or deploy it. So we don't do anything to manage distributed training here. We assume that you bring your own compute infrastructure, but that's something that we want to do in the future. So we've got this API for running projects, and we want to have a pluggable, backend where you can run the project. So right now you can run them locally, but we want to let people plug in their own backend so you can send these projects to our cluster and execute them on there. Yeah.
And another simple question. As I understood, MLflow doesn't have to be coupled to Databricks, right? It's also
doesn't.
open
Yeah.
source.
You can just use it by yourself. You can run a server. You can, you can just run it on your laptop as an individual user. So all these things like where you submit to a cloud service will be sort of extensible plugin interfaces where you can just do something yourself if you want.
Thank you.
Yeah.
Great talk.
Okay.
All right. Thank you very much for a good talk. I have two questions. The first question is that what kind of database format that MLflow supports? Like, do you have a predefined library to connect to, let's say, Spark or let's say other type of database, or do we have to customize it or write it for now?
You're asking about where it stores the metadata, like what kind of database it can use, or?
Yeah, about input data that we can use.
So for input data, your jobs can use any kind of input data because they're just a program with parameters, which can be like a file name or something like that. So you can write a project that, the input data, for example, this one, we say the input data is a path. So all that means is it's just a file. It's just a path on the file system. So you can have whatever type of data you want in there. We don't enforce using a specific data format. Again, in the future, we might put stuff like we might extend this format to say, it's a file with this schema, and we have to it's stored in Parquet format, and then we could do schema validation and so on. But we also want to let you bring in whatever weird format you have. So it's not forcing you to use a specific way. And then for the metadata, where we store all this tracking info, we basically use SQL Alchemy, which is a connector to pretty much any kind of database from Python. So you can use MySQL, you can use Postgres, you can use whatever database you want out there.
Okay.
Yeah.
My last question, you mentioned about model versioning. Does the model versioning support the case where you have the same code, the same data, but you upgrade library, like let's say TensorFlow or something like that?
Yeah, we do track that information on the runs. And so we'll show you that, and you'll be able to say, okay, these two are different because they have a different version. And the model also, I didn't show this in the little example, but the model also can store, which dependencies it had. So it can say which TensorFlow version and so on, so that when you deploy it, we build the right environment for it.
Okay.
Yeah.
Thank you.
Thank you, Matei. There's time for maybe one more question, as long as it's a quick one. Yeah.
Okay. Quick.
Thank you very much for the talk. And to give some background on my question, I run the machine learning platform team at Cruise Automation, and we face a lot of build versus buy questions every day. So my question is specifically about MLflow or anything like open source in general is how extensible do you think the flow is for example, for us to build extension on top of that without, say, having to fork the whole project?
Yeah, it's a great question. Yeah, so we tried to make it very extensible in two ways. So one way is, if you just look at the metadata we store, as I said, it's like these pretty low-level interfaces like files or, for example, tags on a run can be any key value pair you want, and then you can do stuff on top. And there's an API to read all this stuff. Like if you don't like our UI, you can use the API to read stuff and to visualize the results however you want. So that's one of the things we do is it's a general sort of data schema. And then the other thing we do is we have these plugin systems, for example, for authentication and for logging additional information about your environment. Like, for example, when you run it in Databricks, we actually capture a snapshot of the notebook you're in or whatever. That's through this kind of plugin. But if you have your own system where you want to log something special, you can add your own plugin that fires up and that adds that extra information. So we're hoping that people don't have to fork the project. And we're actually working with a lot of companies that are also sort of data platform vendors, like RStudio, and also some smaller sort of data science companies, like the one that contributed the plugin system. And so everyone wants an integration with their own product and their own way of doing it. Some of our customers also use the API to integrate with internal systems. Yeah.
Okay, great. Thank you.
Thank you, Matei.
Great. Cool.